Hello friends, today our concept is the graphical solution of nonlinear programming problem. As in the case of linear programming problem, the graphical method can also be employed to solve the two variables nonlinear programming problem also. In linear programming, the solution is generally a corner point of convex solution space. In nonlinear programming, the optimal solution is not a corner point of the feasible region. Let us see an example. Determine the values of x1 and x2 so as to minimize z equal to x1 square plus x2 square subject to the constraints x1 plus x2 greater than or equal to 8, x1 plus 2x2 greater than or equal to 10, 2x1 plus x2 greater than or equal to 10, and both the decision variables x1 and x2 are non-negative. Here the constraints are all linear and the objective function is nonlinear and it represents a circle. If r is the radius of the circle, then the objective function is z equal to x1 square plus x2 square, which is equal to r square. Our objective is to minimize r so that the circle with the center 0, 0 and radius r touches the solution space. So this is the graphical solution of the given nonlinear programming problem. The first arrow represents the constraint equation of the first constraint. Second arrow represents the equation of second constraint, and third arrow represents the equation of the third constraint. And the solution lies in the first quadrant only. So we have drawn the solution in the first quadrant. So let us see the explanation for this solution. The solution space is bounded by a convex region ABCD. The desired solution point 4, 4 lies on the line x1 plus x2 equal to 8, and this line is the tangent to the circle at the point 4, 4. Since the circle will touch one of the sides of the convex region, one of the sides of the convex solution space would be tangential to the circle. Thus, the solution can be obtained as follows. Now we differentiate the equation of the circle. R square equal to x1 square plus x2 square. If we differentiate this equation, then we get 2x1 into dx1 plus 2x2 into dx2, that is equal to 0 since r square is constant. From this equation we get dx2 by dx1 is equal to minus x1 by x2. Differentiate the constraint equations which forms the four sides of the convex space. First equation, if you differentiate the first equation, then we get dx1 plus dx2 equal to 0. That implies dx2 by dx1 equal to minus 1. And if we differentiate the second equation, we get dx1 plus 2 dx2 equal to 0. That implies dx2 by dx1 is equal to minus 1 by 2. And if we differentiate the third equation, we get dx1 plus 2 dx2 equal to 0. That gives dx2 by dx1 is equal to minus 2. The three solutions can be obtained. Solution 1, from equations 1 and 2, we get minus x1 by x2 is equal to minus 1. That implies x1 equal to x2. First constraint equation is x1 plus x2 equal to 0, and we are having x1 equal to x2. From these two equations, we are having x1 equal to x2 and both are equal to 4. This solution satisfies all the other constraints. If we substitute x1 equal to 4 and x2 equal to 4 in the constraints, then we get x1 plus 2 x2 is equal to 4 plus 8, which is 12, which is greater than or equal to 10. This is true. And 2x1 plus x2 is equal to 2 into 4, that is equal to 8, plus 4 greater than or equal to 10, 12, that is also greater than or equal to greater than 10, which is also true. Hence the solution 4, 4 is feasible. Now let us see the second solution. From equations 1 and 3, we have minus x1 by x2 equal to minus 1 by 2. This implies 2x1 equal to x2. Second constraint equation is 2x1 plus 2x2 equal to 8. From these two equations, we are having x1 equal to 2 and x2 is equal to 4. This solution does not satisfy the other two constraints. Since x1 plus x2 equal to 2 plus 4, which is equal to 10, this is greater than or equal to 10, which is not true. And 2x1 plus x2 equal to 4 plus 4, that is equal to 8. 8 is greater than or equal to 10, which is not true. Hence, the solution 2, 4 is discarded. Next is solution 3. From equations 1 and 4, we have minus x1 by x2 is equal to minus 2. That gives x1 equal to 2x2. First constraint equation is 2x1 plus x2 equal to 10, which implies that 5x2 equal to 10. So hence x2 equal to 2 and x1 is equal to 4. This solution also does not satisfy the other two constraints. Hence the solution 4, 2 is also discarded. Hence the optimal solution is x1 star equal to 4 and x2 star equal to 4. And if we substitute x1 star and x2 star in the objective function, then we get z minimum equal to 4 square plus 4 square, that is equal to 32. That's all. Thank you.